Hello friends, and welcome back to the CMake for JUCE developers video series. My name is Ben Vining, and I am a self-taught C++ developer who loves CMake, so that's why I'm making this video series. In the last video, I covered the basics of the CMake scripting language, and in this video, I'm going to discuss the different types of targets that exist in CMake, and then we're also going to start to apply these concepts by building a basic target. So the first sort of most obvious question here is, what is a target? Simply put, a target is a node of CMake's build graph. So if you have an app that you want to build, your actual executable can be represented as a target. And if your app depends on some libraries, each one of those libraries can be represented as a target. And each one of these targets is how CMake builds its graph of dependencies from one to the other, which it can then translate into things like makefiles or Xcode projects. Each individual target can be large or small. So a target might build just a single source file, or it might be an entire library with hundreds of source files, but either one of those situations could be represented using just a single target. And names must be globally unique. So a target name is just represented as a string in CMake, and each one must be globally unique for the entire build. You cannot have multiple targets with the same name. So there are several different types of targets that CMake understands, and already I mentioned the first type, which is executables. So this is an executable program, either a command line program or a GUI app. CMake just calls both of these things executables. And executables generally are not linked against, so they're basically generally understood to be sort of like the end of the line in terms of like who's going to be consuming it, who's maybe linking against it. From other targets, executables aren't generally linked against, so they're generally like the final thing that you're trying to build in CMake. What you're linking against to build an executable are libraries. So a library is a target that is a collection of source files that can be built and that can be consumed by other targets. So this is basically the core of how encapsulation in CMake works. If you define a library target in one place to build all of your source files for some sort of code library that you're building, then from other places in your build, executables can link against the library target you've defined, and they don't need to have any specific knowledge of those source files or the exact flags they need or stuff like that, because just linking against that library target will propagate all of that information into whatever is linking against it, like your executable. So this is a way that CMake allows you to sort of encapsulate things. There are several different types of library targets in CMake. The first two are shared and static. And so the difference between these two is sort of like a fundamental C++ thing. A shared library is something that is dynamically searched for at runtime by the OS's runtime loader, whereas a static library is something where the code is actually built into the executable, and so nothing needs to happen at runtime. A plugin in JUCE, or really in any build system, is always a shared library. And the reason for this is because when a DAW vendor is compiling their DAW, they're not going to actually copy copies of all the possible plugins into their binary. They're just going to accept dynamically runtime loading of whatever plugins the user wants to use. And so at the build system level, the way this works is they're all shared libraries that the DAW opens using a platform-specific equivalent of something like DL open. And the way that you build something that can be opened that way at runtime in CMake is with a shared library target. On the other hand, static libraries, like I mentioned, are it's also a collection of source files like a shared library, but it's all compiled into the actual executable. So every executable that links against a static library is going to get its own copy of that code basically copied into itself. And there are pros and cons to this. It can lead to larger executables. But on the other hand, because everything was copied into the executable at build time, this can be a bit more stable because there's no chance for example, things like version mismatches happening at runtime with shared libraries. Another type of library in CMake, this one is a little bit less common, but another type of library is an object library. For both shared and static libraries, the way that they actually work is that first the compiler outputs object code.o files, which are then archived into libraries. And if you, for example, want to ship both a shared and static library from the same set of source files, then what you can do is you can create an object library from those source files, which will basically mean that you only have to create the .o files once. Because if you were to create a shared and static library, both from the same set of source files, then each one of those library targets would create its own version of the .o files, basically. But if you want to create both, then you can instead use an object library target, which will create the .o files only once, and then you can have both a shared and static library use the .o files output by this object target, which will basically reduce your compile time. But like I mentioned, that one is less common than shared or static. These are the two main library types that you really need to understand. There is another type of library target called an interface target, an interface library. And what this means is that it's a type of library that nothing actually gets compiled. It's only basically defining a package of usage requirements that can be consumed by someone else elsewhere in the build. So the classic example of this, and something that's been getting really popular in the C++ world these days, is header-only libraries. Damn it. Header-only libraries are defined as interface targets because in C++, if you only have header files and no .cpp files, there's nothing for the compiler to actually compile. And so what you do in CMake for this use case is you define an interface library, which means nothing actually needs to get compiled, but it's still encapsulated because at the place where all those source files are on your file system, you can define all of the source files that go into this interface target. You can define any special properties this target needs to have, any special compiler options, things like that. And then from elsewhere in the build, you can have an executable link against this interface target without needing specific knowledge of what's going on, in the inner workings of this interface target. But again, sort of like a static library, every executable that links against an interface target will build its own copy of that source code because an interface target is only things like header files that don't actually get compiled. You can also have custom targets in CMake. Custom targets are generally targets that don't involve source files, that are not really following this model of compiling some sort of binary code from source files. A custom target is just an arbitrary command that you can execute. So a custom target is a target that when you build it, it executes some sort of shell command. So the really common example of this would be make clean, which CMake does provide. If you're using the make generator, then you can go into the build directory and just type make clean. And what CMake has done is it has used a custom target called clean to execute a script that cleans out any build artifacts that it has generated from previous builds. So that's what a custom target is. It's any arbitrary shell command, and it can be literally anything, any program that can be found on the computer that you're running on. So these are the types of targets in CMake. We have executables, libraries, and custom targets. Within libraries, we have shared, static, object, and interface. Target properties are a key feature of CMake. What you're actually doing as you're creating your build graph and populating it and manipulating it, what you're actually doing is you're changing target properties of all the different targets that you've created. Everything about what a target does and what is needed to build it is defined in its properties. Target properties are a list of key value pairs with both the keys and the values as strings, just like variables in CMake. And like I said, everything about how to build a target is described in its properties. So there are target properties that define what libraries it links against, what compiler flags it has, things like that. So target properties really represent the sort of low-level implementation detail of how to actually create a target at build time. And as you are creating your scripting files, as they're being processed by the CMake interpreter, what it's actually doing is it's manipulating target properties. And then once it has finished executing all of your configuration scripts, then it goes over the entire build graph, and for each target, it looks at what the current state of its properties are. And then that is how it actually generates its build files. And this is an important thing because target properties can be set with a function call in CMake, but there's nothing preventing you from doing this twice. You can set some target property to some value, and then later in your file, you can set it to a different value. And the important takeaway here is that whatever you set last is what's going to win. Because after all your scripting commands have been executed, then CMake is going to actually instantiate the build graph by recursively looking through all of these targets in its graph and the current state of their properties once all of your scripts have been executed. There are commands in CMake for manipulating these directly using get target property or set target properties. Usually you're going to be using some more high-level commands that will do multiple set target properties at once. But there are some properties that you may want to manipulate directly, and that is possible in CMake. Whenever you are setting target properties, there are 3 different keywords that are very important, and these describe the scope of the target property that you're setting. So the simplest case here is private, and what that means is that this target property applies only to me. It's an implementation detail for how to build this target, and no one else who links against me needs to know about this, right? So this might be something like include paths or compiler flags, and this can be completely localized to just one target because not every single person in the build graph is going to need the same include directories or the same compile flags. And so that's why this private target property scope exists. Public means that it's going to set that property for this target that you're calling this on, but also it will propagate to anybody who links against you. So the use case for this is things like if you are creating a library that's going to be linked against, and it defines some header include paths that need to be public instead of private. So for example, if the header include paths are only referenced from this library's CPP files, its implementation, then they can be private because the headers don't need to know anything about them. But if your header files use some sort of external dependency or special, path, then that needs to be declared as public because anybody who links against you and includes your header files is going to need to be able to find whatever those header files include. So that's the difference between public and private. You can essentially think of it as the difference between something that's used only in the implementation, like CPP files, or in the header files as well. And in the first video, I mentioned that learning CMake can lead to a greater understanding of C++ as a language. And this is, I think, an example of that, because the difference between public and private here will make you start to think about what's in your CPP files versus what's in your header files. Because yes, it's all C++ code, but there are actually some important differences and distinctions there between how CPP files get compiled and the way that header files are propagated to anybody who is linking against your compiled CPP files. There is another keyword here, interface, and this is mostly for use with interface targets. Like I said before, interface targets are not actually compiling anything themselves. They're just a package of things that can then be consumed by other targets. And so if you have an interface target, you'll use the interface keyword with functions that need a scope, because that lets them know that this property is only being propagated outward to people linking against you. It's not actually populating your target properties. And CMake handles the transitivity here for you. So you can declare private or public target properties, compile options, include paths, anything like that. And as CMake is actually generating the build system, once it's evaluated all your scripting commands and it's time to actually write the makefile or the Xcode project, anything like that, then it traverses the entire tree of targets, and anytime it finds a dependency, it says library A depends on library B, it will go and look at library B, and for all of its public target properties, it will copy those values over to library A, because library A is consuming library B. And so these scope keywords here are a very, very powerful tool and a powerful way to allow you to basically just specify your build requirements using the private keyword and your usage requirements using the public keyword, and let CMake handle the actual propagation of all these things outward transitively. Targets in CMake are somewhat like objects. So we have constructors. CMake has commands add library, add executable, add custom target, and these all introduce a new target into CMake's build graph. So those are somewhat like constructors. And then we can think of target properties sort of like data members of these target objects. And then we have member functions. So like I said before, we have set target properties or get target property. These are basically like accessor functions to the data members. And then we have these commands here, which what these commands all do is they manipulate various properties of the target, but they are slightly higher level. They allow you to be a bit more expressive with your intent by saying target link libraries, include directories, or compile definitions, compile options, or you can add source files to a target. But what every single one of these commands does internally is basically call set target properties. It basically manipulates properties of whatever target you are working on. And there are no destructors. Targets in CMake, once they have been created, they cannot be destroyed. And so thinking about targets like objects in this way, if you've ever used a C API that sort of wants to pretend that it's object-oriented, where you'll have some sort of function that creates it and then returns a pointer to this object, and then every time you want to do something with it, you pass in a pointer to this object. That's somewhat like how the CMake API with targets works, because basically anytime you're calling one of these quote-unquote member functions, you're going to pass the name of the target simply as a string. It's not really a pointer, it's just a string describing the name of the target, but it's conceptually similar to working with a C API in that way. So now that we've talked about the various types of targets, let's actually apply some of this. So this is a very, very basic Hello World program here in C++. Like you've probably seen millions of times before, I'm just going to print hello world and return success. So this is all that's really needed to build this project in CMake. The first command here, CMake minimum required, what this does is this tells CMake, I'm writing this project for, at minimum, CMake version 3.21. And so then as CMake is running, when it gets to this command, it can know, all right, if I am older than version 3.21, then it can warn the user, or I've actually said I want to make it an error if it is a too old version of CMake. And then here in the project command, I discussed this a little bit in my last video about the CMake language, but the first argument here is simply the name of the project, which doesn't have to be the same as a target name, but in this case it is. This could be, something else. And then the version of the project, the languages you're going to use, and then you can provide a description. The languages keyword here, what this is actually going to do is enable the C++ compiler. You could do it separately. There's a different command for that. You could do this. CMake provides this command, enable language, which basically what this does is it searches for a working C++ compiler and it tries to compile a very small project, probably something very much like this. But it basically just ensures that the compiler works, and if it doesn't, then it will give an error message and stop processing. And so that's all done here in this project command with the languages keyword. And so the first sort of hello world here, this is going to be a command line executable that I want to run. And it takes no input. It's simply going to print hello world. So all I'm going to do is I'm going to add an executable here called hello world. And what this command does is it adds a target called hello world that is an executable. And this file here, main.cpp, is all of our code for this. So I'm going to call this function target sources with main.cpp to add that file to this target. And then you'll see here that I'm using the private keyword. As I discussed before, this could be public or interface, but private is the appropriate one to use here because I'm building an executable and nothing is going to link against this. Nothing else in the build craft needs to know about this source file. It's simply an implementation detail of this target, so it needs to be private for this target. And something else I want to mention, this variable, CMake current list dir, what this is the absolute path to the current file being processed, which in this case is this CMake lists.txt. So CMake always sets this variable for you automatically. And so if I want the absolute path to main.cpp, this is how I can do it, because this basically gives me my current working directory that I'm in, and then I just say main.cpp from there. However, the target sources command automatically evaluates relative paths relative to the current directory. So this is exactly the same as what I had before. I can just say main.cpp and it will automatically look in the current directory. Down here, I'm setting some target properties on hello world. I'm really just setting the version to be the same as the project version. So that allows me to, if I make improvements to this someday, then up here I can just change the version in one place and it will change this property on this target down below. And this can be useful in larger projects if you have multiple targets. You may want to version them individually, which is certainly possible, but I usually prefer to use the project version like this. And this is another automatic variable that CMake defines for you. So after you call this project command here, when you provide a version, then it populates variables project version and then project version major, minor, and patch, which is very convenient because you don't need to do any sort of like save this to a variable and then pass the value of that variable here. It's not necessary because it's automatically defined for you after this project command. This so version here, this is a little bit more advanced. This has to do with the file name that's generated for the runtime loader, which I always just kind of set it out of habit, and maybe I'll go more in depth into that in a future video, but for now, don't worry about that too much. I'm basically just setting some version information here. And so I'm in this directory here, and we can go ahead and create our build files just by running this command. The -b here just means that I want to write the build files into this directory, builds. And it's generally recommended to use a directory that's not the same as your source directory. So that's why I passed this -b builds. And then the CMake executable will assume that the source directory is whatever the current directory is. And so as we can see here, CMake has generated for us a make file in the builds directory. And so if we wanted to, we could come in here and then say make hello world, and we can see that it has built. But like I mentioned in my first video, CMake also provides this command line syntax, which allows you to invoke whatever build tool was generated for. And so what I'm doing here is I'm saying build, and then I'm providing the build directory, and then I'm going to say target hello world. It's the only thing in our project at the moment, so I don't really need to specify that, but just to demonstrate how you can select a target to build, and this works. And so as we can see in our builds directory, it has created this output file. This is our actual executable here, and when we run this, we can see, as expected, we get hello world. So this is sort of like step one of creating a CMake project. But let's say that maybe we want to consolidate some of this code into a reusable library. So let's say that I've got my namespace here. I've just added 2 files. It's going to be a very, very small library, but I'm just going to create a function in here that's going to be, it's just going to print out hello world for me. All right. So now from main, all I need to do is I'm going to include hello.h, and then I'm going to call this function print hello, and then return success. And this should do the exact same thing because we're printing hello world from this function that we're now calling. And instead of building all of this code into the executable, I want to demonstrate how we can build this into a library. So I'm going to create a library. It's going to be called print hello, and I'm going to make this a static library for now. And I'm going to add my source files to this library. So I'm going to say that these are public. The public one is going to be my header file, and the private one is going to be hello.cpp. So again, the CPP file is simply implementation. Anybody who wants to use my print hello library doesn't need to know anything about what happens in hello.cpp. All they have to care about is my header file here. And that's basically what I've said here with this command. I've declared the header file as public and the CPP file as private. So this means that anybody who links against print hello is going to get hello.h added to their header files, which I will show you what that looks like in Xcode in a moment. But the last thing I need to do here is target include directories to make sure that whoever links against me can actually find this this hello.h file. And so because this is in the same directory, I can just put the CMake current list dir here. And again, this is public because anybody who links against me needs to be able to find this hello.h file, which is also public. And now down here, I'm going to link hello world, the executable, to print hello. So what this means is that hello world is an executable target, and it is going to consume the print hello library. And this is private because the executable itself, nothing needs to link against it. So this fact that it consumes print hello is basically just an implementation detail. If this were another library whose header files referenced print hello, then this would need to be a public dependency. But this should be everything we need. So we've got main.cpp here, which is our hello world executable, and then we have hello.cpp and .h, which have been added to our print hello target, and then we're linking here, and so this should all work. So let me rerun CMake, and it worked. And then I'm going to say build builds. So basically build everything in the builds directory. And as we can see, I got some errors here. Let's see why that was. And that was because I didn't include IOStream here. So this should fix that. And it did. No. Namespace. But one thing to notice here for the iteration process is that I can call CMake build without regenerating the project files. And the reason why that is because the actual CMake script didn't change between builds. All I was changing was the actual C++ source code, and it already knows about these files. So when they've changed, it can just use the same build files that were already generated. Those don't need to change. And this target built successfully. So now we can go into here and we can see that we have the same hello world file as before and this libprinthello.a file. So this is the archive that was created from our static library print hello. And I can execute this and it prints hello world just as we expect. The last thing I want to demonstrate in this video is, let's say that we've got, a project structure somewhat like this. We've got an executable, we've got a library. Now let's say that I want to put the library into a subdirectory. I want to clean up my source tree a little bit and sort of reorganize things. That is very well supported by CMake. These file paths have changed, they don't exist anymore. And so the way that you do this is by adding a CMake lists.txt file to your subdirectory. As I mentioned in the last video, anytime you invoke CMake in a directory or add a directory to the build, this file is considered the entry point for that directory. So both for the top level project and for the subdirectory, the CMake lists.txt file is considered the entry point. And so I just moved this code into this CMake lists.txt file. I'm now creating this library in this subdirectory, adding the source files and specifying include directories all in this subdirectory. And CMake has this command, add subdirectory, and I'm simply going to pass the name of the subdirectory. And I'm going to leave all this executable stuff in the top level directory. And so now if I regenerate CMake, Now what we can see is that our builds tree looks a little bit different. We still have a make file here, but now we have a libhello folder. And if we go in here, there's another make file. And this is basically the way CMake works. Every time you add a subdirectory is added in the build tree. So the build tree basically mimics the layout of the source tree in this way. And again, I can build, and now we see that I have my hello world artifact here in the top level build directory. And if I go into libhello, that's where my archive is for this static library. So that is a very basic primer to CMake. We have added a static library and an executable target. We have put our static library into a subdirectory. We've talked about manipulating target properties using target sources, target include directories, target link libraries, and here I'm directly calling set target properties with some version information. And we have talked about public, private, and interface scope keywords for all of these operations. And just to reiterate, private means that this is an implementation detail. So because hello world is an executable, nothing else is going to link against it. And so that's why this is private, because anything it needs is basically an implementation detail that no one else in the build graph needs knowledge of. But here in this library, this include directory is public, because if somebody links against this library, I want them to be able to find this header file. And so this is public. The very last thing I want to do is demonstrate what this looks like in an IDE. So I can call this same command, -b builds, but now I'm going to add the -g parameter. And what this does is it specifies the CMake generator. And now as I enter the builds directory, you can see here that I've got an Xcode project instead of a make file. And when we open all of this, I can go ahead and build this, and this succeeds. But as you can see here, each target was basically added as its own folder in the source browser here. And so this is my library. But as you can see in hello world, this target here, I've got main.cpp, but it also added this header file, hello.h. And the reason that is because in this library, I declared hello.h as a public source file. And then in my executable, I consume print hello. And so the public source files were added to this executable, which makes it very convenient to, I can now see the header file for this library that I am linking against. And so that is just a basic overview of different types of targets in CMake. We have built a Hello World program. We have demonstrated working with CMake with both makefiles and Xcode. And hopefully this is a pretty good overview of the basics and fundamentals of how CMake works as a build system. In our next video, we're going to actually build a JUCE project. And I'm going to kind of explain a bit more about how all of these core concepts of targets and target properties are actually implemented by JUCE, and how those are sort of translated to the JUCE world. So thank you for watching, and I will see you next time.